Right, this video has solutions to problems 11 through 20. So let's take a look at number 11. Here we're given a graph of a polynomial function with real coefficients. All local extrema of the function are shown in the graph. So here we're for part A, we are going to identify the interval or intervals where the function is increasing and or decreasing. Notice there's no parts of the function that are constant. So we're going to label this. Again, we always need to label our answers. Increasing, we always read a graph from left to right. So increasing is where the graph is going uphill from left to right. So that's going to happen here, 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 and here. I'll just draw an arrow here. So the intervals where our function is increasing is from negative infinity, we only want the x values, to -6. You can put commas or you could put union, and we're going to go from -4 to -1, and then from 3 to 6, and then from 8 to infinity. Decreasing, where a function is going downhill, so it's going to be here, here, and here. So that's going to be from -6 to -4, from -1 to 3, and then from 6 to 8. So again, you could put commas or the union symbol. B, at which x values does a function have a local max? So we have a local max here, here, and here. So what x values are those? -6, -1, and 6. What is the sign of the leading coefficient? One end is going down, the other end is going up. So it's definitely an odd function. And so for odd functions where the left side falls and the right side rises, we have a positive leading coefficient. So for C, leading coefficient is positive. D, what is the smallest value of the degree of the function? It should say, what is the smallest value of, or the degree of the function could be. Sorry about that. So if you look at the turning points, we have 1 turning point, 2 turning points, 3, 4, 5, 6. So it's going to be 7. Because a degree should always be 1 more than the number of turning points. Okay, for number 12, we're given 2 functions f of x and g of x. We want to find the following operations or compositions. So for A, this notation means f of x times g of x. So this means x plus 3, this quantity, times 2x squared. So we're just going to distribute the 2x squared. So we're going to get a 2x cubed plus a 6x squared. For B, f plus g of x means f of x plus g of x. So this becomes x plus 3 plus 2x squared, and there's really nothing we can do with it. You could write it 2x squared plus x plus 3, but that's it. For C, f minus g of -1 means f of -1 minus g of -1. So f of -1 becomes -1 plus 3 minus g of -1 is 2 times -1 squared. So we're going to get a 2 minus 2 times 1, that's 2 minus 2, so that's 0. And then for D, this is g of f of x, so we could also rewrite it this way. So this becomes g of x plus 3, so we get 2 times the quantity x plus 3 squared. So this becomes 2 times the quantity x plus 3 times x plus 3. I'm going to multiply the 2 binomials together, so we're going to get an x squared. On the outside, we'll get 3x. Inside, we'll get 3x. So that's 6x plus 9. Then I'll distribute the 2. So we get 2x squared plus 12x plus 18. Okay, for 13, h of x is equal to x minus 6, and g of x is equal to the product of these two binomials. So for a, we want to find h divided by g of 5. So this becomes h of 5 divided by g of 5. So h of 5 is 5 minus 6. G of 5 becomes a quantity 5 plus 5 times 5 minus 2. So up top we'll get a negative 1. Then we'll get 10 times 3. So we get negative 1 over 30. Negative 1/30. For b, find all values not in the domain of h divided by g of x. So again, this just becomes h of x over g of x, which is x minus 6 over x plus 5, x minus 2. We multiply together. So again, we're looking at our denominators, and we just say x cannot equal a negative 5 or a positive 2. So negative 5 and 2 are not in the domain of h over g of x. All right, for 14, this time we're not asked to graph this, but we just need to use it to evaluate these expressions at these x values. So g of negative 5, where would negative 5 be? Well, we use the first one as long as x is not equal to negative 2. We use the second one if x is equal to negative 2. So negative 5 is not equal to negative 2, so we use the first one, so this becomes 1/2 times negative 5 plus 1. So we get a negative 5/2 plus 1. You can get common denominators. You could turn that into a negative 2.5. So we get a negative 3/2. G of negative 2, we use this one right here because x is equal to negative 2, so that's just negative 3. And then g of 3, we're back to using the first one because 3 is not negative 2. So we get 1/2 times 3 plus 1. So we'll get 3/2, getting common denominators, 2/2. So we'll get 5/2. All right, here we're asked to graph. Again, you can make a table of values. Now, because we have to take the square root, when we subtract 3, we want a nice perfect square. So let's see what happens here. What is our domain? So that could be helpful. The domain means x minus 3 needs to be greater than or equal to 0. So we need all x values greater than or equal to 3. So I'm just going to start with 3. Or if we look at a translation, it's the graph of y equals the square root of x translated 3 units to the right. So here's our starting point. Our leftmost point is going to start right here. I cannot pick any x values to the left of this. So let's do 3. Let's do 4, because 4 minus 3 is 1, and we can take the square root of that. Let's do 7, because 7 minus 3 is 4. We could take the square root of that. And then that might be all that we can, I said let's get one more point up there, if possible. So here we have square root of 3 minus 3, that gives us 0. So that is our first point. Now we're going to have 4 minus 3, that's going to be square root of 1, which is 1. 7 minus 3, square root of 4, so that'll give us 2. Now, if you're doing this on graph paper, you could fit a little bit more. I'm going to have to go off my coordinate plane a little bit. So let's do 12. Because 12 minus 3 is 9. Square root of 9 will give us 3. So I'm just going off 2 more squares. So that might be right here and about right there. So there's 12, 3. So there's our graph. Okay, 16, we are graphing another piecewise function. Again, I'm just numbering by ones here, the way up to 10. All right, so both of these are linear functions. So first I need to graph y equals 3x plus 1 for all x values less than negative 2. So again, I may have to go back and erase, but where is this going to start? It's going to start at positive 1. And I'm going to go up 3. My slope is 3, so I'm going to go up 3 over 1. Well, I can't go that way. I need to stay less than the negative 2, which is right here. So I'm just going to go in the opposite direction. I'm going to go down 3 and over 1 this way. I still can't include any of these points yet. I'm going to go down 3 and over 1 again, and that's where negative 2 starts, but it's not included, so I need an open point. I'm going to go down 3 again and over 1, and that's going to be enough. So I need to erase these points. And I'm going to draw a line like this. Okay, for the next one, it's y equals x minus 3. So that's going to start as long as x is greater than or equal to negative 2. So I'm going to start down here at negative 3. And my slope is positive 1, so that means I'm going to go up 1 over 1, up 1 over 1. But I need to go down to negative 2, so I need to go down 1, negative 1, or down 1 over 1 to the left, down 1 over 1 to the left. So now it looks like this. Graph this line. So here's our piecewise function. Now this is continuous, because where it was open for the green line, it is now closed in for the red. So this is continuous. I can draw the whole thing without lifting my pencil up. All right, we're going to take a look at another graph. This is like number 1, I believe. I'm sorry, number 3. But again, we're graphing the parent function. You can make a table of values. We can use translations. But here's my parent function. Again, vertex is at 0, 0. Go over 1, up 1, over 2, up 4 on either side. So here's y is equal to x squared. So now y equals 3 times the quantity x plus 1 squared plus 4. This is going to shift 1 unit to the right and up 4. Now a is 3, so that's going to help us when we go to count. So now my vertex is at negative 1. I'm sorry, not 1 unit to the right, 1 unit to the left. And up 4. So our vertex is negative 1, 4. And with a being 3, we can make a table of values. So I've got negative 1, 4 in the middle here. So let's go negative 2, negative 3, 0, and 1. I'm going to start with 0 and 1 because those are easier to substitute in. So I'm going back up to this. So 0 plus 1 is 1. 1 squared is 1. 1 times 3 is 3. 3 plus 4 is going to give us 7. Next we'll have 1 plus 1 is 2. 2 squared is 4. 4 times 3 is 12. 12 plus 4 is 16. And then we'll have symmetry here and here. So again, if you're doing this on graph paper, you have the ability to go up a little bit higher. If this were a test, I would definitely give you a coordinate plane large enough to graph this. All right, so we need to go 0, 7. So in other words, if I go over 1, 1 squared is 1, but now I need to triple it, so I'm going up 3. And if we go over to 1, we're going up 16, so I would actually put us like right up here on either side. So we have a very narrow parabola. And this is y is equal to 3 times the quantity x plus 1 squared plus 4. All right, here we have, notice it's x cubed, we have a cubic function to graph. And again, we can make a table of values, especially for this one. And I'm just going to start with something very basic. I just want to go from negative 2, negative 1, 0, 1, and 2. So let's do the easiest one. 0 is going to be 0. I'll substitute these other values in. So here we're going to have negative 7/4. 2 cubed is 8, so I'm going to put 8 over 1. So this will give me 4 goes into 8. We can do it this way. 4 goes into 4 one time, 4 goes into 8 twice, so we're going to get a negative 14. If I substitute in a -1, actually -2 cubed is a -8, so it's going to make it a +14. -7/4 times -1 cubed will be -7/4 times a -1, which is 7/4. Over here, we'll have -7/4 times 1 cubed, which will give us a -7/4. And then this becomes -7/4 times 2 cubed, which is 8, which will give us a -14. So we have 0, 0. We have 1 and -7/4. So this is actually -1 3/4. We have a 2 and a -14. So that'll put us right about here. We have a -1 and 7/4, so right about here. And then we have a -2 and a 14. So that'll put us right up here. All right, for 19, we're testing for some symmetry. It says for each equation, determine whether its graph is symmetric with respect to the x-axis, the y-axis, and or the origin. So if we're looking at A, what I need to show is that I'm going to substitute in the opposite of x. So we'll test for the x-axis first, then the y-axis, and then the origin. So for the x-axis, for testing for symmetry with respect to the x-axis, the x values stay the same, but y's are the opposite. So I want to leave in the same x value, but I want to substitute in the opposite of y. So this becomes 32x to the fourth still. Now negative y to the fourth is still going to turn out to be y to the fourth, so then we get plus 34y to the fourth, which equals 37. And we're going to say this is the same. So symmetric, we just do with respect to WRT, the x-axis. The y-axis, y values stay the same, x values are the opposite. So we'll do 32 negative x to the fourth plus 34y to the fourth equals 37. Same thing is going to happen here. Because it's an even exponent here, we're just going to get 32x to the fourth plus 34y to the fourth equals 37. Same. So symmetric with respect to the y-axis. Now for the origin, if we got yeses to both of these, it's symmetric with respect to the origin, but we still need to show this. We need to substitute in both the opposite of x and opposite of y. So we get 32 times negative x to the fourth plus 34 times negative y to the fourth equals 37. So we still get 32x to the fourth plus 34y to the fourth equals 37. And we're just going to draw an arrow back to this as well. Say it's the same. Therefore, we have symmetry with respect to the origin. All right, let's take a look at B. Okay, so let's do the x-axis. Leave the x is the same, substitute in the opposite of y. There's nothing else we can do. This is not the same. So you would say not symmetric with respect to the x-axis. For the y-axis, leave y the same, substitute in the opposite of x. This is what we want to show. And negative x to the fourth is going to be the same as x to the fourth, so we would say this is the same. Therefore, this is symmetric with respect to the y-axis. Now, if we only have symmetry to one of these, we would expect this to not be symmetric with respect to the origin. So let's go ahead and test this, though, show this. We'd have to substitute in the opposite of both. You'd still see that we would have the opposite of y, but the rest of this would stay the same, so we would do not the same. Therefore, not symmetric with respect to the origin. All right, so you guys had a problem very similar to this on the activity 4, and I was a little bit lenient on that, but make sure you're clearly answering what's being asked here. So we're going to use synthetic division. We want to specifically identify the quotient and the remainder. So our shelf number is actually going to be a positive 6. Take a look at our powers here. We have 4, 3, 2, 1, and then 0 there, so we don't have to put in any zeros as place fillers. So we're going to have a negative 2, an 11, a 6, a 1, and a 3. So dropping the negative 2 down, 6 times negative 2 is negative 12. 11 plus a negative 12 will give us a negative 1. Then we'll get a negative 6. We'll get a 0. 6 times 0 is 0. We'll get a 1. 6 times 1 is 6. And we'll have a 9. So here we would say that the quotient is negative 2. Since it started off with x to the 4th, we're down to an x cubed, minus x squared, plus a 0x, so we don't write it, plus 1. And then the remainder is going to be 9. So I'm just specifically asking for the quotient and remainder. Yes, if you had to write this out all together, it would be all of this plus 9 over x minus 6. But I'm just looking for you to identify the quotient and the remainder.